Hello, everyone. At this point, you've responded, or should have responded, to the discussion question looking at what infinity means to you. And we'll have your own definition for infinity. I mean, really, infinity is a reference to forever. It's not a fixed number, it's counting forever and ever and ever and ever. Now, one thing that is interesting about infinity is that it can converge to a finite value. Now, to give you an example of what this might mean, I want you to take a look at what's called the Fibonacci series. And Fibonacci series is a really simple series to work out. Basically, the first two values are 1 and 1, and then all you do to get the next value is add the previous two. So for this line, the sum of 1 plus 1 is 2. The sum of 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 8 plus 5 is 13. 8 plus 13, 21, and so forth. And you can see I've just done a simple calculation in this Excel spreadsheet, or Google spreadsheet in this case, of just add the previous two numbers. Now, what's interesting about this is that even though this series goes on forever, in fact, it starts to move into really gigantic numbers really fast. So just by row 117, I'm already up to 23 digits. The quotient of each consecutive Fibonacci number actually starts to become a constant value. So if we take a look, for example, at 1 divided by 1, well, obviously that works out to be 1, right? If I do that same calculation on to 2 divided by 1, well, 2 divided by 1 is 2. Continue on, 3 divided by 2 is 1.5. 5 divided by 3 is 1.67-ish. 8 divided by 5 is 1.6-ish. 13 divided by 8 is 1.6-ish. And you can actually see as I start to move down, the numbers start to converge. They start to actually become a constant value. And in fact, once I get a little bit further down, you'll see that the numbers will actually converge to a constant value. And by row 27, at least to the number of digits we're showing, they stop changing. Now, of course, as we make these numbers bigger, then the difference between these numbers gets smaller. And so the quotient starts to become even closer. And so even though we only have 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places shown here, then these numbers are still changing as you get further and further down the decimal point. And in fact, the bigger the numbers are, the closer to a single number these things get. Although, just like the number pi, this number contains an unrepeating set of decimals. It's what's called a transcendental number, that you can basically calculate an infinite number of decimals and see no repeating within that. Now, this is kind of interesting because now, if I continue that forward, you can see that as I get further and further down, you don't see any changes at all. And we call that tendency on a series convergence. And if we take a look at what this looks like as a graph, you start to see that even though at the beginning it really has a lot of variance, starting with 1, moving up to 2, down to 1.5, 1.6, and starting to oscillate back and forth, the value that it's oscillating around, a value we call an asymptote, and we'll talk more about that moving forward, starts to turn into a constant value. And in fact, that particular value, the 1.6 and so forth, has a special name, and it's something you can feel free to take a look for. It's called the golden ratio, and it shows up in nature all over the place.